Hello all, welcome to this session. Hope I am audible.
Good evening, sir.
Yes, sir.
Yeah,
Good evening,
good
sir.
evening all. Right, so Sunday we had session 1 on week 10, and this is second session on week 10. And tomorrow we have Solve with us for week 10. Okay, so week 10 is all about new world, which is complex world, which we can't see in real life. Right, so we have introduced you guys to the complex world, and there are many properties that we discussed on Sunday. Unfortunately, recording is not made, I guess. Right, but those who have attended would have known what all we discussed in that. Right, so today we will be continuing where we left in the last session. So we will be talking about the trigonometric functions, which are mainly the sinusoids, right? Sine and cos. And we have introduced it, I hope, and we all know. But let us quickly do this, and then we will discuss two beautiful things. One is Euler's formula, and the other one is roots of unity. Okay, so we'll spend some more time on these two things, and we'll solve problems after that. If you have any doubts in week 10, you can ask me and we can solve it. Okay, and tomorrow is the solve with us session, and we will be discussing week 10 related problems, and Tia will be coming up with some 10-15 problems, and she will discuss. Okay, and tomorrow is the deadline for week 10. I hope all of you are aware of it. And next Wednesday, we have the deadline for both week 11 and week 12. Okay, so we can't extend week 12 even by one day. Okay, so right after you finish week 10, I suggest you guys start watching week 11, finish week 11 as early as possible, and then start week 12 also. All right, so even though didn't they will not account for your GA score, it will be helpful for you uh, for the end term exam. Okay, so yeah, any doubts before we begin?
No, sir.
No, all right,
No, sir.
all right. So let's do this real quick because we have been studying these trigonometric functions from our childhood, right? So we have sine theta and we have cos theta, and these two are almost, not almost, they are almost the same, right? They are just the shifted versions of one of the other. Right, so if I have to plot sine theta, how will that look? It will pass from the origin and it will have nice wavy curve. And we all know sine theta is an odd function, right? From the graph also you can see. And this is sine theta. And what is the derivative of sine theta? That is what we are going to see now graphically. Okay, so I hope we all know this, right? So derivative of sine theta with respect to theta is cos theta. Am I correct?
Yes, sir.
Ah. So this we would have studied it as formula, or we would have by hearted this. And but how does this came? Derivative is basically the slope at every point, right? So if you see the slope at 0 for sine theta, you can see, right? If you draw the slope tangent at point 0, you can see it will be y is equals to x, and slope of y is equals to x line is 1, right? So therefore at 0 the slope is 1. And if you see, if you move to the right, after every point, the slope will decrease. It will decrease. So you can see, you can draw the tangent line. It will decrease, and at point pi by 2, the slope of sine theta will be 0. Slope of sine theta, not the value. Okay. So at pi by 2, sine theta takes value 1, but it is the local maxima point. Yes, recall the properties of local maxima. Since it is local maxima point, if I draw the tangent, that will be parallel to x-axis and the slope will be 0. So the slope starts from 1 and slowly it comes to 0. Right? If I just plot the slope curve, it is starting from 1 and at pi by 2 it comes to 0. So something like this. Right? So right after pi by 2, you see the slope tangent lines will start having negative slopes. Right? So which are tangents of will be like this, right? Slide towards the left side, and the slopes are negative, and it will be negative starting from 0. The slope will decrease, and slowly at pi it will have -1. The slope will be -1. It is y is equals to minus x line. Right? The graph I drew was not accurate, but if you see, you can easily see that at pi the slope will be -1. But if you draw the tangent line, it will be parallel to y is equals to minus x line. Okay, so that means it will start from 0 and it will come to -1 at pi. And again, you will see that from this -1, the slope will increase, and at by you reach 3 pi by 2, it will become 0 again. So like this, if you just plot the slope curve, you will start seeing like this. Okay, and this dotted line is nothing but dotted curve is nothing but cos theta. So that means if I see the slope, right, which is d sine theta by d theta, is nothing but cos theta. And if you see the curves, both the curves are just the shifted versions of each other. So you shift the curve sine theta by pi by 2 to the left. Okay, so sine theta you shift towards left, you will get cos theta. Or if you shift cos theta to the right by pi by 2, you will get sine theta. Right, so from there you can write two identities. Right, you shift your signal by pi by 2, you will get cos theta. Pi by 2 to the left, so it is theta plus pi by 2. And if you shift cos theta to the right, it will give you sine theta. And you can rewrite this as, so cos of theta minus pi by 2 is nothing but cos pi by 2 minus theta, because cos is even function. So cos pi by 2 minus theta is sine theta. Right, and if you replace theta by pi by 2 minus theta here, so you replace some phi is equals to pi by 2 minus theta. Right, then theta becomes pi by 2 minus phi. And if you substitute it, you will get cos of pi by 2 minus pi by 2 minus theta. Sorry, phi is equals to sine pi by 2 minus phi. Right, so the left hand side will simply become cos phi, which is sine pi by 2 minus theta, phi. Okay, you replace phi by theta, nothing changes. Okay, so this is one identity and this is the other identity. And you would have learned these identities in your schools or colleges, but you would have learned it as an identity and you would have by hearted it. But this is how you prove them graphically. Okay, and in the same lines, the derivative of cos theta will be minus sine theta, and also you can prove this or visualize this graphically. Maybe I will leave it as an exercise for you guys. You plot the cos theta and see the slopes of the slope at every point, and you plot the slopes at every point, and you will see that it will just be the negative of sine theta. It will not be sine theta. You will get an inverted with respect to x-axis graph. Okay, so maybe you can all try this out. Okay, you can keep this as an exercise. All right, so you can try it out. Yeah, and then professor has discussed this analytically. He has proved this identities, but I don't want to do the same thing what professor has done. So I have shown you graphical proof. So whichever you like, these are the two identities you have to remember. If you remember, great, good. But if you forgot also, so these are the ways to prove them. Okay, so once we understood the derivative of sine theta is cos theta and the derivative of cos theta is minus sine theta, we can talk about higher order derivatives of the same trigonometric functions. And once we introduce higher order derivatives, we can define the Taylor series expansion of sine theta and cos theta. Right, so let's say you have a function f of x to be sine x and g of x to be cos x. Okay, so now we'll do this parallelly. The derivative, first derivative of f of x is cos theta, which is cos x. Right, so the derivative of sine x is cos x. If I take the derivative of this derivative function, which is the second derivative, now the derivative of cos x is minus sine x. Right, I can take the third derivative. Now derivative of sine x is cos x. So the derivative of minus sine x is minus cos x. So the minus comes out and it will just be minus cos x. Now if I can take one more derivative, which is the fourth derivative. So these are the higher derivatives, right? So fourth derivative, I have to take the derivative of minus cos x. Cos x derivative is minus sin x. So minus of minus sin x will become sin x again. So you see we came back to sin x. So after four derivatives, so we started with sin x. We took the derivative. We got cos x. We took one more derivative. We got minus sin x. We took one more derivative, minus cos x. And then we took fourth derivative, which gave back sin x. And you can repeat this. So fifth derivative will just be cos x. Right? So this will just alter between sin x, cos x, minus sin x, minus cos x. Right? So like this, you can take n number of derivatives like this. And if I come to g of x function, if I take the derivative of g of x, it will be cos x derivative is minus sin x. And if I take one more derivative, minus sin x derivative will be sin x derivative is cos x, so minus sin x will be minus cos x. So like this, third derivative will be sin x and fourth derivative will be cos x. So here also, after 4 derivatives, we got our function back. Right, so then it will just repeat. Right, so this will just become minus sin x and so on. Okay, so now once we know the higher order derivatives, we can write the Taylor series approximation of these functions around x is equals to 0. Because we know the values at all the values at x is equals to 0, all the higher order derivative values at x is equals to 0. So we can write the Taylor series expansion. Okay, so the Taylor series expansion of sine slash cos around x is equals to 0. So when I say around x is equals to 0, so we have to compute all the derivatives, higher order derivatives at point 0. So let us write the Taylor series expansion first and then we'll see. So any function h of x, if I have to write the Taylor series around x is equals to 0, it will be h of 0 plus h first derivative divided by 1 factorial into x minus 0, right, plus h double derivative at 0 divided by 2 factorial x minus 0 whole square and so on, h nth derivative at 0 divided by n factorial into x minus 0 whole power n and so on. Right, so this will be the Taylor series expansion for any function h of x at around 0. Right. What we need? We need the function value at 0. We need the first derivative at 0. We need all the higher order derivatives at point 0. So let's see, do we have this or not in sine and cos? So if I just scroll up, since f of x is sine x, right? So this implies f of 0 is 0 because sine 0 is 0 and f prime of x is cos x. So I substitute 0 here, I'll get cos 0 is 1. So f prime of 0 is 1. And then f double prime. If I substitute 0 here, I'll get sine 0, which is 0, minus of 0 is 0. So this will be 0. And the third derivative is minus cos x. If I substitute 0 here, the third derivative value at 0 will be minus 1. And then you will see a pattern. So all the even derivatives along with the function value will become 0. And all the odd derivatives will oscillate between 1 and minus 1. Right, so fifth derivative is again 1. And sixth derivative will be 0, seventh derivative will be minus 1. And this will form a pattern. Okay, so what is the pattern? Can anyone identify? How can I write this compactly? Okay, pure silence. So do you all understand what I'm trying to convey? No? Okay, am I audible?
Yes, sir.
Okay,
Yes, sir.
okay, great. Thanks. So what we are trying to do is we are trying to find the Taylor series expansion of sine and cos. Okay. So for that we need the function value along with its derivatives at 0 because we are finding the Taylor series expansion around 0. Okay, so for that, whatever the knowledge we have about this derivatives of the sine x and cos x, we are using that and we are finding all the derivative values at 0. Okay, and we found out that for sine x, f of 0, f of 0, f double prime of 0, f fourth derivative of 0, and f sixth derivative of 0, like this, all the even derivatives became 0. So it will become 0. You can cross check it. It will be either sin x or minus sin x. At 0, sin x and minus sin x both are zeros. So this I can compactly write as you take any even derivative, like 2k. 2k is always even for any k. Right? You take any even derivative at 0, it will be 0. Right? So for any k. For any k equals to 1, 2, 3, even 0 also. 0 is like function value. Okay, so this is okay. For any odd value, you see, for any odd, f prime and f fifth derivative and then f ninth derivative. So if you solve for more derivative values at 0, you'll see 1, 5, 9, every fourth odd derivative, you
It
will
will be
see that
1.
it will give you 1,
Yes, sir.
right? And then f triple prime of 0, f seventh prime of 0. Again, there will be a difference of 4, f 11th prime of 0. All this will give
It will give
minus 1,
minus 1.
right? So we got all the derivative values at 0, right? If you just simply substitute that. So if my function is sine x, if h of x is sine x, then h of 0 is 0 plus h prime of 0. So the first derivative is 1. So 1 times x by 1 factorial, and we don't have double derivatives, so even derivatives you can skip. Then you will have h triple prime of 0 is minus 1, so you will have minus 1 by 3 factorial into x power cube, and then you will not have fourth derivative value at 0 because it will be 0, so since it is even. You will have fifth derivative value. Fifth derivative value is 1, right? So you'll have plus 1 by 5 factorial into x power 5. And then like this, if you follow the pattern, you'll see that minus 1 by 7 factorial into x power 7 plus 1 by 9 factorial into x power 9 and so on. So you'll have next minus 1 by 11 factorial into x power. So you'll only have the odd powers, right? So you can write this as x minus x cube by 3 factorial. You would have seen this, but it would have come out of nowhere, right? Like it's like a magical formula which you have by heart. But this is the proof for that. Okay. And so on. And this is the Taylor series expansion of the trigonometric function sin x. Like this, you can also do it for cos x. And for cos x again, you just follow the same steps that we followed for sine and substitute them here. Take h of x to be cos x. You compute cos 0, first derivative of cos 0, second derivative of cos 0, and so on. And the Taylor series expansion turns out to be 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial plus x power 8 by 8 factorial and so on. Okay. Yes. Yes, Nitish.
Do with x equal to pi by 2, and I have noticed an observation like if we do at x equal to pi by 2 with sin x, it is equal to around x equal to 0 in cos x function, and vice versa.
Yeah. Yeah, that's how it should be, no? Sin pi by 2 is cos 0. So you are saying that you have done this experiment by substituting pi by 2 and 0 and you got both same.
Yes, sir.
Okay, great. Alright, so these are the Taylor series expansions of sine and cos. And why did I bring this up here? Because whatever I am going to discuss within 2-3 minutes, you will understand. So it is all about Euler's formula. Okay. So till now, okay, is it clear?
Yes, sir.
Yes, sir.
Okay, nice. So now what we will do is we'll go back to our complex part. Okay, so we have took a diversion and learned this trigonometric functions and its derivatives. So we are going to use them now. And how are we going to use them is the follows. So if I have to define something like e power z, where z is a complex number, z is some x plus iy, right? So if I have to define this e power z for z is equals to x plus iy, how can I do this? I substitute z as x plus iy and use the properties of exponentials. I will get e power x into e power iy. And I know how to evaluate e power x. So we have studied that earlier. But how to evaluate this e power iy? Right? So that has become a challenge now. But if I know the Taylor series expansion of e power x, I can also do Taylor series expansion for e power iy. Nothing changes, right? So we know e power x where x is real. So x and y are real. Okay, so they are not complex. So x and y are real, z is the complex number. And e power x, where x is real, we know the Taylor series expansion around 0, 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. Right, so if it is for complex, all I need to know is how does e power iy look. If I know how does e power iy look, then I am pretty much happy, right? Because e power iy, instead of x, I'll try to use iy now in the same above formula. If I do that, I'll get 1 plus iy plus iy whole square by 2 factorial plus iy whole cube by 3 factorial plus and so on. Okay, so if I got this, then I know I square is -1, I can substitute that, right? So I is a complex number which is square root -1, or in other words, the actual way to define this I is when I take the square of this complex number I gives me -1. Okay, so this is one good way to represent I square. Define I. Okay, so once I know this I square is -1, I cube will be minus I and I power 4 will be 1. Right, so I is square root -1, I square is -1, I cube is I power 4 is 1. Okay, so if you substitute it, what we'll get is 1 plus iy, we can't do anything for this, plus iy whole square is I square y square by 2 factorial plus I cube y cube by 3 factorial plus I power 4 y power 4 by 4 factorial plus I power 5 y power 5 by 5 factorial plus and so on. Right, so if I simplify this using that I square is equals to -1, I cube is equals to minus I, a little bit of simplification if I do, I will get 1 plus iy plus I square is -1, so I will have minus y square by 2 factorial. I cube is minus I, so we'll have minus I y cube by 3 factorial, and then I power 4 is 1, so we'll have y power 4 by 4 factorial, and I power 5, again you can repeat this. So I power 4 is 1, so I power 5 you can write it as I power 4 into I, so it is 1 into I, it will be y I. So I y power 5 by 5 factorial and so on. Now you see there are some complex terms, right? So every odd power has a complex complex term I, whereas even terms doesn't have it. So you can rewrite this as some a plus ib form. So you bring all the real terms on one side, all the complex terms on the other side, and you pull out I common, and what we'll get is 1 minus y square by 2 factorial plus y power 4 by 4 factorial, and then if you proceed further you will see that you will have y power 6 by 6 factorial plus y power 8 by 8 factorial minus and so on will be your even terms, will be your real terms, and you pull out I out in all the odd terms, you will see that the resulting will be I of y minus y cube by 3 factorial plus y power 5 by 5 factorial minus y power 7 by 7 factorial and so on. And if you just scroll up and see the Taylor series expansions for sine and cos, you will see that this whole real part
Is
is
cos
just the Taylor series expansion of cos x, cos y. Right, so here we have variable y. So this is just cos y. And if you see the complex term,
that's sine y.
that is sine's Taylor series expansion. So e power iy, we can write it as cos y plus I sine y. And this is the Euler's formula. Okay, instead of y, you replace it with the theta or x or whatever. E power I variable can be expressed as the real part will be cos y and the complex part will be sine y. Now once I know this, I can express. So remember earlier we started with this. Can I find this? Right, e power some complex number. And we can find that e power x into e power iy. And e power iy we know it is cos y plus I sin y. So this will just be e power x cos y plus I sin y. And then this will be e power x into cos y plus I e power x into sin y. So e power complex number will also be a complex number and it is expressed as the real term plus I into the complex term. Right, so this e power x into cos y is the real term, e power x into sin y is the complex term of e power z, where z is a complex number. Okay, so right, so this is the imaginary part and this is the real part of the complex number e power z. Okay, so and from this we will derive the most beautiful result in the field of mathematics or in the world of mathematics is the following. Okay, so you substitute y is equals to pi. Okay, so we have e power iy as cos y plus I sin y, right? So if I substitute pi, what will I get? E power I pi on the left hand side, and on the right hand side it will be cos pi plus I sin pi. So we all know sin pi is 0. So the complex, there is no imaginary part at all. Right, so the only real part, and the real part will also be equals to -1. And why is it most beautiful result is because you see E is a transcendental number. I is an imaginary number. And pi is also again a transcendental number. So the combination of the transcendentals and the imaginary turns out to be an integer, not even real number, not even a rational number. It turns out to be an integer and it is equals to -1. So yeah, so this is the beauty of the math equation. One of the beautiful math equation. Okay, then you can appreciate the result, but we'll also use these results in various places. Okay, so I hope Euler's formula and this particular result is clear to all of you. All right. Now let's talk about the roots of unity. Right. So this is also not a very difficult concept, but since we learned the complex numbers, it's always good to talk about this roots of unity also, and especially cubed root of unity. Right, so what are these roots of unity? So you create a simple polynomials of the form x power n is equals to 1, and you vary n. You start from 1, 2, 3, 4 and so on. Right, so the simple cases we would have seen this x square is equals to -1, which is a quadratic equation, right, and its roots are x is equals to plus or minus 1, right. So some variable power n that gives us 1, and we are going to solve that, and the roots of that particular equation are called the roots of unity. So this is the second root of unity because the power is 2, and the most famous one is this cubed root of unity. Okay, so which is x cube is equals to 1. So x cube is equals to 1. You can rewrite this as x cube minus 1 is equals to 0. And then you can pull out, you can use a cube minus b cube formula, and you can write this as x minus 1 into x square plus x plus 1 is equals to 0. And then from here, you can say x is equals to 1 is one root. But the other root is x square plus x plus 1 is equals to 0. If you solve this, we will encounter two complex numbers which are conjugate to each other. Right, so one is -1 plus root 3i by 2, and the other one is -1 minus root 3i by 2. So these are the cubed root of unities. Okay, so there are three roots. X is equals to 1, x is equals to -1 plus root 3i by 2, and -1 minus root 3i by 2. And we often denote this -1 plus root 3i by 2 as omega. Okay, so we call, whenever we say cubed root of unity, we were talking about omega. So omega is -1 plus root 3i by 2. Surprisingly, if you compute omega square, what do you think it will be?
It will be -1 minus root 3i by 2.
Yes, so the other root. So you will get the other root,
Yes, sir.
-1 minus root 3 I by 2. And if you compute omega cube, you will get 1.
Yes,
Because
sir.
omega is the cubed root of unity. So that means if you cube the root, you will get 1. So it should satisfy the condition, right? So that is why omega cube will give you 1. And as I said, usually whenever we say cubed root of unity, when we are talking about, when we say omega be the cubed root of unity, we are referring to this particular expression. So omega is -1 plus root 3i by 2. Okay. So like this you can proceed. Right, you can compute omega power 4, fourth root of unity. Sorry, not omega. X power 4, fourth root of unity is x power 4 is equals to 1. So here also it's a 4-degree polynomial, 4-degree polynomial equation, which is x power 4 minus 1 is equals to 0. You use a power 4 minus b power 4 formula, which is similar to a square minus b square. You will get x square minus 1 into x square plus 1. Right, so x square minus 1 is equals to 0, or x square plus 1 is equals to. Right, so with x square minus 1 is equals to 0, the roots can be either plus or minus 1. Whereas here it is x square is equals to -1. It is more or less I square being -1. Right? So x could be plus I or minus I. Right? So even if you square I, you will get -1. Even if you square minus I, you will get -1. So therefore the roots, fourth root of unity are -1 plus 1 I minus I. So these are the four roots of unity. So like this, can we generalize this? Can we compute the nth root of unity? Right, so that's the question. Okay, so to understand this, we will go back to the unit circle. Okay, and see how this unit circle on complex plane, not on the real plane. So let's draw a unit circle. Okay, so let us say this is the unit circle. Now if I am looking at only two roots of unity, so let me label this. So this is the real part. This is the imaginary part. Okay, so if I draw the unit circle, this is 1, this is I, this is -1, this is
minus.
right. So now if I just look at the two roots of unity, they are 1 and -1. Only these two. If I look at cubed root of unity, 1, so -1, so the other root will be here and the third root will be here. Maybe I will plot them. So with the violet we will represent two roots of unity with which are on the real part. Right? Whereas if I look at the cubed root of unity, which will start from 1, but the second point is here, which is -1 plus root 3i by 2. And the third point will be here, which will be -1 minus root 3i by 2. Right? So these are the 3 points. If I plot the 4 roots of unity, one will be there, one is always there. So it is violet, yellow, blue, everything is there at 1. And I is there. And -1 is there. And minus I is there. Now you should be seeing some pattern here, right? So if there are only two roots of unity, both are equidistant from on the circle, right? So 1 and -1 are equidistant to each other, right? So from here to here and from here to here, the arc length or the distance is the same. If it is cubed root of unity, here to here, here to here, and here to here, all three arc lengths are the same. If it is fourth root of unity, so there are 4 points on this circle which are equidistant from each other along that circle, right? So if I had some 5 points, I would have 1, 2, 3, 4, 5. So which will be equidistant to each other. Right? So all the 5 points will be equidistant to each other. In other words, you see with respect to angle. Okay, so this is 360-degree angle. Right? So at the center. If I have only, if I am looking at the only second root of unity. Yeah. So this arc makes 180 degrees. The other arc makes 180 degrees. If I have cubed root of unity, so you draw these 3 lines and you see it makes 120 degrees, 120 degrees, 120 degrees. Right? So yeah. So for nth root of unity, you divide the arc into n parts. Like this. And there will always be one in it. Right? So even if you look at x power n, so nth root of unity is the roots of the polynomial equation, which is x power n is equals to 1. So if I just substitute 1, it will be 1 power n, which is 1, is equals to 1. So 1 will always satisfy for any n. Right? So therefore, the 1 will be the first root always. So you start from 1. If it is cubed root of unity, then you divide the arc into 3 equal parts. And then wherever the division is happening, those will be your 2 other roots. If it is 4, then you divide the arc into 4 equal parts. Then wherever the division is happening, those will be our roots of unity, fourth root of unity. Right. So now let's dig little bit deeper. So 1 I can write this as e power I into 2 pi. So why 2 pi? 2 pi is 360 degrees. Right. So pi is 180. So 2 pi is 360. So e power I 2 pi is 1. Now, similar way, in the similar fashion, I can write this I as e power I two pi by 4. Right, so 2 pi by 4. Right, so yeah. So this minus 1 is e power I, sorry. Am I missing something?
Odd pi, sir.
Sorry, I didn't get it. Power?
E to power odd pi.
Can you repeat? Odd pi. Okay. Yeah. So this is e to the power I 2 pi by 4. And this will be e to the power I 2 pi by 4 into 2. Right, so this is e power I pi actually. So this is e power I 2 pi by 4 into 1. This is into 2. And this minus I is e power I 2 pi by 4 into 3.
Multiplied by 3.
And you can just do e to the power I 2 pi multiplied by 4. 2 pi by 4 into 4. Right, so what we got is basically for fourth root of unity, we took e power 2 pi by 4 and looked at the powers of it. Right, so for fourth root of these are the fourth root of unities. Fourth root of unities are, one is e power I 2 pi by 4 into 1, and another one is e power I 2 pi by 4 into 2, another one is e power I 2 pi by 4 into 3, and the last one is e power I 2 pi by 4 into 4. Right, so using the properties of exponentials again, so you can always take the power. Right, so these are nothing but, so it is another way of writing, that's it. Into 3 is same as a power b whole power c is same as a power bc. So that's what I wrote. Whole power 4. So now what is this e power I pi by 4 is basically fourth root of e power I into 2 pi. Right, so this fourth root of e power I 2 pi and their powers are the roots of unity. Okay, so this whole power 1, whole power 2, whole power 3, whole power 4 are the 4 roots of unity. So like that, if I just write the nth root of unity, I'll take e power I into 2 pi, nth root of this will be my first root, and then nth root of e I 2 pi whole square will be the second, nth root e power I 2 pi whole cube will be the third, and so on. So the last root will be nth root of e power I 2 pi whole power n. So which will be 1. Right, so this is 1, and all these are the nth roots of unities. And you can compactly write this as, again, so here power 1, power 2, power 3, power 4 and so on. It's floating, power is floating. So you can write this as e power I 2 pi. So that power you can take it inside some k, and this nth root. Okay, so these are the nth roots of unities where k goes from 1, 2, 3 and so on, n, or you start from 0. Okay, so there is nothing difference. You start from 0, 1, 2, 3
Minus 1.
to n minus 1. You go till
Yes,
n
sir.
minus 1. So there is no difference. You either you start from 1 or you go till n, or you start from 0 and go till n minus 1. Whichever you choose. So if you choose this way, you will get 1 at last. If you choose this way, you will get 1. You will start with 1 and you will go till the n minus 1. Okay, so these are the nth root of unities. Okay, and again, so why do we learn this? So there are few problems which involve these roots of unities to simplify the complex expressions. Okay, so for that we use the ideas of this nth roots of unities. And as mentioned, so among all these nth roots of unities, cubed root of unity and fourth root of unities are much popular. Okay, so with that, I think we kind of winded up week 10. Okay, so I think, yeah, so we have done all the theory. So if you guys have any doubts in any of the practice assignments, activity questions in week 10, we can discuss. And tomorrow is the problem solving session on week 10. So we'll come up with some nice formula, nice problems, and we'll solve them. Okay. Anything else you can ask?
Sir, I
Yeah.
have a doubt in activity 10.2, the last one.
Just a second. Activity 10.2. Last one.
Yes, sir, the fifth one.
Okay. So consider three polynomials. Okay, so P1 of x is x square plus x plus 1. P2 of x is x cube plus x square plus 1. And P3 of x is x cube plus x plus 1. Okay. So what is the doubt? So what do you want to know here? Any particular option or all the options?
Sir, here, how to approach this question, the real roots, I'm not getting
Okay.
it.
Okay. So that's a nice question. So quadratic, it's very easy, right? So P1 of x, I don't think there are any issues
No, sir,
because
that P1x, I have no issues.
yeah. So x square plus x plus 1 will be like this, I guess, right? Which will not have any real root, right? So, and quadratic is the only polynomial, not only quadratic, there are even degree polynomials may never touch x-axis at all. Okay, so this is real axis again. Okay, so this is x and this is y. Okay, so quadratics can be like this. So either like that or like this. They can have these kind of graphs where it may never touch x-axis at all. Whereas when you try to plot 3-degree polynomial, okay, or odd degree polynomials. Okay, so what do you think will happen to odd degree polynomials?
It touches at least one point in
It will
x-axis.
touch at, yes, sir,
Yeah.
it will touch,
So you
intersect at
can't
one.
have a cubic polynomial where your both ends are on one side, right? So like quadratic. So in quadratic, if you see plus infinite or minus infinite, both can go to plus infinite or both can go to minus infinite. Whereas a cubic polynomial, because of this x cube term, okay, since that is the leading term, when x goes to infinite, it will be the dominant term and it will go to infinite. When x goes to minus infinite, x cube will go to minus infinite. So that means cubic polynomial at x infinite, it should go to infinite. At x minus infinite, it should go to minus infinite. And in between, the graph will be somehow, but it is continuous. So x cube plus x square plus 1 is a polynomial, nice cubic polynomial, right? So it will, there will not be any breaks. So there will not, it will not be like this, and then there is a break and it goes like this. So it can't happen like that, right? So it's a nice polynomial. So minus infinite, and then it has to go to plus infinite. So somewhere it has to cross the x-axis, right? So without crossing x-axis, it can't go to plus infinite. So that means you can always say that a cubic polynomial will have at least one real root. Right, so this is a graphical proof, but it has a very nice proof. You can prove it. A cubic polynomial will have at least one real root. So I'm not saying again it has only one real root. Either it can have one real root and two complex roots, or it can have all three real roots. Okay, so here, and also if it has only one real root, the other two roots will be complex conjugates to each other. So that is also there. So if it has only one real root, then the other two roots are complex conjugates to each other. Okay, so one will be A and another one will be Z and another one will be Z bar. Okay, if it is cubic polynomial. Not only cubic polynomial, even if it is 5th degree polynomial or 7th degree polynomial. So all these odd degree polynomials will have at least one real root. Okay, so in that way, you can see this, and x cube plus x square plus 1, you can plot that also roughly, right? So you know how x square plus 1 looks. So x square plus 1 is a quadratic like this, and you have x cube also, you know x cube also, which will be like this. And if you add these two, so our expression is basically x cube plus x square plus 1, right? So if you are adding these two, you can clearly see, so these two gets added up, and x cube is dominant, so this will get inverted, and the resulting graph would somewhat look like this. And you can see this is the place where this x cube plus x square plus 1 intersects x-axis. Therefore, you can say it has only one real root, not more than one. Similarly, x cube plus x plus 1 also you can see. Right, so x plus 1 is a straight line, and you add x cube to it, and you will see it will only touch at 1. Okay, so these are all simple skills that you should always learn. Okay, so whenever polynomial or some expression is given to you, you should roughly able to plot the curves. Okay, I hope that's all you need. Once if you know P2 has one real root, P3 has one other real root, P1 times P2 times P3 will have two real roots, and P1 into P2 into P3 will have a degree of 8, and it will have 8 roots, including the complex. Okay?
Yes, sir, got it.
Yeah. All right. Any other? Okay. PA question 10. Right. So, all right, we'll do that. That's a good question actually. So, okay. So here also it is given, you see, omega is a complex cubed root of unity. Right. So what does it mean is omega cube is 1. Okay. And also not only that, since omega is the cubed root of unity, you can write this as omega cube minus 1 is 0. And then you will see omega minus 1 into omega square plus omega plus 1 is equals to 0. And as I mentioned, omega is not 1. So even though they said complex cube root of unity, omega is not 1. Omega is that minus 1 plus root 3i by 2. So this cannot be 0. So this will be 0. So if omega is the cube root of unity, we have derived a nice identity, which is omega square plus omega plus 1 gives us 0. Okay, so why I bought this is because we will use this to simplify the given expression a bit. So the given expression was 1 into 2 minus omega into 2 minus omega square plus 2 into 3 minus omega, 3 minus omega square plus 3 into 4 minus omega, 4 minus omega square plus and so on, plus n minus 1 into n minus omega into n minus omega square. Right, so this will just take this expression and simplify this. This will be 1 into 2 into 2 will be 4, or it will be 2 square. Right, I'll write it in squares. 2 square minus 2 omega minus 2 omega square plus omega cube. Right, so this will be the expression. And then you look at the inside one. So this is minus 2 of, so the same identity, I'll write this as omega square plus omega is minus 1. Okay, so here you can see minus 2 omega square. If you pull out 2, you will have omega plus omega square. I can replace it with minus 1. So minus 2 into minus 1 will become plus 2. So we will get 1 into 2 square plus 2 plus omega cube is 1. Right, so omega is the cube root of unity, it will just be 1. Right, so what we have is the inside 2 square plus 2 plus 1. So 2 minus omega into 2 minus omega square is just 2 square plus 2 plus 1. So similarly, this second one will just become 2 into
3 square
3 square
plus 3 plus
plus
1.
3
Plus 3 plus 1.
plus 1. Similarly, 3 into 4 square plus 4 plus 1 plus and so on. Okay, so I will separate this out. So what I will have is 1 into 2 square plus 1 into 2 plus 1 plus 2 into 3 square plus 2 into 3 plus 2 plus 3 into 4 square plus 3 into 4 plus 3 and so on. So now you see this last terms 1, 2, 3 and so on. So you know how to add them, right? So it is just 1, 2, 3 and the last term is, you can write the last term also. I missed it. So it will just be n minus 1 into n square plus n plus 1. So it will just be n minus 1. So like this, it will just be n minus 1 into n square plus n minus 1 into n plus n minus 1. So this will just come to n minus 1. So that is n minus 1 into n in n divided by 2. It is just the sum of 1 to n minus 1. Right, so that is okay. So what about the other expressions? Can we do something about it?
1 into 2 square, 2 into 3 square, then we can use the sigma formula.
Yes, sir. So I will write this as summation
k is equals to 1 to n minus 1 k into k plus 1 whole square, or should I do k is equals to 2 to n k minus 1 into k square. So I can do this, right? So this is for the red terms. So like this one. So all I have clubbed them together, and I started from k is equals to 2 to k is equals to n, k minus 1 into k square. Similarly, I think I can do it for 1 into 2, 2 into 3, 3 into 4 things also. So summation k is equals to 2 to n, k minus 1 into k. Right, so I can do this also. Plus, I have this 1 plus 2 plus and so on, and so that will be n minus 1 into n by 2. I don't want to disturb that. Here I can again see split the summation. I'll have summation k is equals to 2 to n k cube minus summation k is equals to 2 to n k square. So k minus 1 into k square is k cube minus k square. So here it will be plus summation k is equals to 2 to n k square minus summation k is equals to 2 n k. So here we can see this and this will get cancelled out. All we have is summation k is equals to 2 to n k cube. So do we know the formula, or can we compute this? Anybody? N cube, summation to n cube. Am I correct? This is correct, right? No?
Yes, sir, it's correct.
Okay, so summation n is equals to 1 or k is equals to 1 to n and k cube will be n square
N square, n plus 1 का
whole square by 4.
whole divided by 4.
Right, so that will be the formula. But here we are starting from k is equals to 2. So therefore this will be n square into n plus 1 whole
Plus
square divided by 4 minus 1. So you have to subtract 1 from it. And then here also we are summing from k is equals to 2 to n. So here also we can do minus n into n plus 1 divided
whole
by
divided
2.
by 2 minus 1.
Minus 1
And
will,
yes,
minus of
it will
minus will
get
just
minus
become
of minus
plus.
of plus 1. Yes, sir.
So n minus 1 into n divided by 2. Right, so this and this will get cancelled out. And then we have, we will just do,
Sir, one more minus one.
sorry,
One more minus one.
why?
Here is k sigma of k 2 to n.
That only this minus 1, no? Minus 1 became plus 1 because there is minus outside.
I'm talking about the third part where sigma of k where k belongs to 2 to n.
This one, no?
Yes, sir.
So that is only this thing, this one. Because, okay, if you write minus, it will just go in the bracket, right? So if you write minus, this is how it will be. And if you open the brackets, minus and minus will become plus, and this will get cancelled out. So there is no k square terms at all. K square will get cancelled out. So there is only k cube, which will be these two, and there is only k, which will be these two. And there is n minus 1 into n by 2, which is the last three 1, 2, 3, 4, and so on to n minus 1. Okay, so this is correct only. And now this is like n square into n plus 1 whole square by 4 minus 2n n plus 1 divided by 4 plus 2n minus 1 into n divided by 4. Okay, so now the denominators are the same, so numerators you can pull them together. N whole divided by 4. So now you expand the numerator and take some terms common. I think we can clearly see n is common in all the terms. So you can pull out n, and then there will be n into n plus 1 whole square minus. Did we miss anything? Okay, looks like no. So you pull out n, this will be my 2 times n plus 1 plus 2 times n minus 1 divided by 4. Now minus 2n. So you can see, you can simplify this. I think n into n plus 1 whole square minus 2n minus 2 plus 2n minus 2. So again there will be some cancellations. This and this will get cancelled out. Right, so we'll have something like n into n square plus n 2n plus 1 minus 2 is minus 4 divided by 4 n of n cube plus 2n square plus n minus 4. What did we miss? I think we are not getting the same expression. Did we miss something? So something is missing, right? What is that missing? K square minus k cube minus k square. Okay, what if we write in this way? Instead of starting from k is equals to 2, k is equals to 1 until n minus 1. And this is k, and this is k, and this is k plus 1 whole square. Right, so will it matter? This is again n minus 1. This is also k into k plus 1. Okay, if it is like this, What will it change? Nothing, no? Let's see. So this will just be summation k is equals to 1 to n minus 1 k into k square plus 2k plus 1 plus k square plus k. Okay, so this will just be summation k is equals to 1 to n minus 1 k cube plus 2k square plus k square plus 3k square plus 2k. Right, so k is equals to 1 to n minus 1, k cube will be n minus 1
n minus 1 whole square.
n minus 1 whole square into n square divided by 4 plus k square will be n minus 1
n minus
into
1
n
n minus 2
and then
2n minus 1.
2n minus 1, na?
Yes, sir.
2n minus
Hold
1
it.
divided by
Hold 6.
6, no? And then
So 2 of n minus 1. The nth term is here n minus 1.
2 of n minus 1.
Yes. And plus 1.
N
Plus 1.
plus 1. Yeah, yeah.
Yes.
2 of n minus 1 plus 1. Then there is 2k. K is running from 1 to n minus 1. So we'll have 2 into n minus 1 into n divided by 2 plus n minus 1.
Sir, we have to multiply with 3
Yes, sir.
in
In
second.
the second term, we
In the
will
second
multiply
one,
with
we have to
by 3.
multiply with 3. And then this will be n minus 1 into n divided by 2. Right, so
And in the second term, previously I have also written this correct expression. It will be n minus 1 whole into n, 2n minus 1.
2n minus 1,
Yes,
yeah. 2
yes, sir.
times, yeah, minus
It will
2,
be
yeah.
same. Yes, sir.
Yeah, it will be same. So this 3 and this will become 2. And now we can take n minus 1 and n common, which is what the expressions in the options look like. And if I pull out n and n minus 1, we will have n minus 1 into n. And then we'll have plus 2 times 2n minus 1. Because n minus 1 goes out, n goes out, but denominator is 2, so I have to multiply it by 2 in the numerator, and 2n minus 1 is left. Plus 2 plus 1, sorry, plus again 2 into 2 I'll have 4, and again 2 I'll have whole divided by 4. And if you just simplify this, n into n minus 1 into n square minus n plus 4n minus 2 plus 4 plus 2 divided by 4.
Sir, plus 2 instead of 4.
Which one?
And at the place of 4, we have multiplied by 2 with 1. So we get 2, not 4.
Yes, sir.
Sorry, we get multiplied by 1.
By 2 into 2n minus 1 plus 2, not 4. Sir.
2 into 2n minus 1 plus 2, is it?
Plus 2. Yes, sir.
Why is it plus 2? Here we have
Because
2,
we
no?
multiply by 2 with 1. 2 multiply 1 is equal to 2.
So the denominator is 2, right? I have to make the denominator to 4, right?
Yeah, to make a denominator 4, we have to multiply by 2 in numerator. So we multiply with 1 with 2, then we get 2, not 4.
Okay, just a second. So I'm writing for this expression. This expression, I have to make the denominator 4, right? So n and n minus 1 gone out. I didn't pull out this 2 out, right? And in order to make the denominator 4, I have to multiply 2 with 2, right? Which gives me 4. And here, I'll have to multiply 1 with 2, which gives me 2. No?
Yes, sir. That's correct.
Yes, no? Yeah, this 2 and this 2 will get cancelled out. And we'll have the final expression to be n into n minus 1 into n square minus n plus 4n is plus 3n
3n plus 4
plus 4
divided by 4.
all divided by 4.
Yes, sir. Correct.
Yeah. So this will be the expression. So it's better to write starting from k is equals to 1 to n minus 1 rather than starting from k is equals to 2 to n. I don't know why it didn't work. Maybe I did a small calculation mistake. It should also work. Okay, so it doesn't matter how you start. Like either you start from 2 to k, 2 to n, or 1 to n minus 1. It should not affect much. But I think final expression would be the same, I guess. So maybe while I am taking the common, I would have missed some term earlier. But this is how you can do. Okay, so we use this idea. Okay, alright, so finally I think we reached to the answer somehow.
Sir, I have a question just from my curiosity, not related to any activity question, but related to another cube root.
Hmm.
My question is in nth root of unity, we just expression x to power n is equal to 1, and we can easily imagine a circle with the radius of unity on complex plane. But what about when we talk about x to power n is equal to minus 1? Is it logical to think, can we represent like x to power n equal to 1 on complex plane?
Good. Okay, so for everything we'll start from basic only. So let's start with 2. So x square is equals to minus 1 is plus or minus I, right?
Yes, sir.
Yes, sir.
Then x cube is equals to minus 1. So this is x is plus or minus I. X cube is equals to minus 1. We'll have one root as minus 1, right? Because minus 1 whole cube is minus 1. And the other two roots, x square minus x plus 1 is equals to 0. If you solve this, 1 plus or minus square root b square is 1 minus 4 is square root 3i divided by 2.
Yes,
Okay.
sir.
So if you just plot this, no? So what are we going to see? So for the first two roots, is for the second, second root of minus unity. So first two roots stand like this, and the second, the cubed thing will come like minus 1 is there, and this is there. Right, and if you move further, to think of x power 4 being minus 1, then x power 4 plus 1 is equals to 0. And what are the roots for this?
One
1 minus 1, I and
minus
minus 1.
No. 1 is not a root. 1 power 4 is not minus 1. I is also not a root. I power 4 is also 1. Minus I is also 1. So it is square root of minus I. So what is square root of I? Good discussion. I itself is square root of minus 1, right? So what is square root of I? Can I express square root of I as some a plus ib?
Yes, sir.
Yes,
It's
sir.
also a complex number.
Sorry?
Yes, sir. It can also a complex number. Then we can just write like this.
Yeah, it will be a complex number, of course.
Yeah.
And how to get to that? I can write it as e power I pi by 2. Right? Euler's
Yes, sir.
formula.
Yes, sir.
And then taking square root is nothing but it is e power I pi by 4. So this is square root I. And e power I pi by 4 is cos pi by 4. Again, Euler's formula. I sin pi by 4. This will be 1 by root 2 plus
Plus I by root 2.
I by root 2. So our solutions for this
So
will
e to
be
power iota pi by 2 is a real number because pi by 2 in sin x is 0.
sin pi by 2 is 1, no?
Sorry.
That. Yeah. So for 4, what you will get is this exact center points. So this, and this. So 1 by root 2 plus I 1 by root 2, 1 by root 2 minus I 1 by root 2, minus 1 by root 2 plus I by root 2, minus 1 by root 2 minus I by root 2. So you'll get these 4. Okay. So even this is also making sense, but yeah, this also makes sense to see.
Yes,
Even this
sir. So we
also,
can also, yes, sir.
yeah,
We
this
can
also divides the arc into
end parts.
equal
But
parts.
how can we compute the negative radius if we're talking about the representation on complex number as a circle?
Huh. So it should not be called as a negative radius. Rather, you look it as an equation itself. Right? So something like that maybe. So you are solving an equation. So it should not be connected to something like you are looking on a radius which has magnitude 1.
Sir, if I'm not wrong, mathematics don't allow us to put any representation, any figure with negative radius.
Yes, this is not negative radius. So that is what I meant, no? So x
Uh,
power n is equals to minus 1. It should not be seen as the points on the radius minus 1. So it is just an expression, equation. Did you get the point?
yes, sir.
So x power n is equals to minus 1 is making sense visually. But if you say x power n is equals to minus 1 are the points on the unit circle where minus 1 represents the radius, then it's not. It doesn't make sense. Okay?
Yes, sir.
Yeah. But nice. Good. Keep it up. Maybe even I will also learn together with you.
Thank
All
you, sir.
right. Yeah. Any other doubts?
No, sir.
Okay. So then we'll meet tomorrow. We'll do some problems. Okay. So with that, we are going to close week 10 and we are going to start week 11 on Friday. Not Friday, I think Friday is an holiday. So please check the calendar and join the sessions accordingly. Okay. So all right. Thanks all for joining and have a great day. Bye.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.